we have this weirdo infinite sum, and I gave you the infinite sum you probably know, which is 1 plus x squared and so on. It might actually even be even more helpful to remember why this infinite sum equals 1 over 1 minus x, because that technique will help you do this. Do you guys remember what is the trick to show that this equals that one?
Oh, you have another sequence and then you minus, subtract.
Yes, okay, this is great, yeah. This is a trick that everybody should know, including, I think I did this proof in my business math class. So everybody should know this trick, which is, I don't know, is there some room somewhere on this page I can sneak it in? Okay, I guess it's going to go here. So if you want to do 1 plus x squared plus x cubed plus dot dot dot, you give it a name, you call it s, and then you write another copy of s underneath, which is 1 plus x squared plus dot dot dot. But then what you do is if you multiply it by x, then that will shift everything by 1. So 1 will become x. So x times s is not 1 plus x plus x squared. It starts with x, right? So the 1 gets multiplied by x. The x gets multiplied by x. The x squared gets multiplied by x, and so on. And you end up with a shifted copy. And the point of this is now that you've shifted everything over, things are lined up where you have a bunch of terms in s, you have a bunch of terms in xs that are the same, and sort of the nastiness of s and the nastiness of xs are the same, so now you subtract them from each other. So you do a big minus sign, and on the left-hand side you have 1 minus 0 is 1, but all the other things cancel. So x minus x is nothing, x squared minus x squared is nothing, x cubed minus x cubed is nothing, so you have plus 0 plus 0 plus 0, and then on the left-hand side you have, after subtracting, let's put the minus sign over here, you have 1 minus x copies of s. So 1 minus x copies of s is 1, and therefore s equals 1 over 1 minus x. And okay, if you wanted to actually make this rigorous, you would have to do it up to n, and then keep track of how big is the error, and argue that the error goes to 0, and all that jazz. So actually, if you do it up to n, you would have an x to the n over here, and you have an x to the n plus 1 over here. So all your zeros would end with x to the n plus 1. So you would get a correction term, x to the n plus 1 over 1 minus x, I believe with a minus sign, because it got subtracted. But I'm not asking you about that term for now, I'm just asking you about the first term. So that was for 1 plus x squared. And then what I'm asking you guys to work on, or try to do, is what do you do with 0 plus 1 times x plus 2 times x squared plus 3 times x cubed. So the first one is called the geometric series or geometric sequence, the sum of a geometric sequence or a geometric series. And the second one is sometimes called an arithmetico-geometric, because it's got a little bit of both arithmetic and geometric. And there's many ways to do it, but one way is to try to apply the same trick. So write down s is the sum, then do some manipulations with s and see what you can get out. And yeah, all of this will really sort of make sense of why we're doing this in the course. In a minute, you're going to see that last class we were finishing up with this Fejer kernel, which was the sum of the cosines, but the sum of the cosines with these weird coefficients. And if you look at these coefficients, they go 1, 2, 3, 4, 5. So actually the sum we're going to have to do, finding a nice formula for this, is essentially doing the kind of sum that I'm having you do in the warm-up problem. And once you do that, you'll get a nice formula for this whole thing, which is surprising that there would be one. In the same way, it's kind of surprising that there's a nice formula for this. Okay, so that's the warm-up problem. I'll give you guys a few more minutes to try it. You do have to get a pen and paper and sort of sweat for a little, but let's see if you can get the right answer. Okay, I'll give you a few more minutes. I'm not sure, maybe some people voted too early. Do you guys want me to reset it? Does anybody, or nobody, okay, nobody's putting it in. I'll wait then until we have some more votes, and then we'll take it up and go from there. Yeah, right? Well, for this term, I think I have to continue to write it. Next term, I can tell the students on the first day. Okay, we're up to 4 answers. Maybe I'll wait one more minute or 2 more minutes, and then we'll go from there. Okay, we're at 1 person left. I have 5 answers out of 6. Okay. All right. Okay. So everybody's answered. Let's take a look at what you guys said, and let me try to zoom out here. But okay. Yeah, with labels displayed. Oh yeah. You know, I've never tried this. Let's try. What does this do? Oh, this is pretty cool. Oh, what a great feature. So 4 people voted for something. I love that. Okay. Okay. So most people voted for this one. 1 over 1 minus x squared minus 1 minus x. And I think that one is correct. So if you chose that one, that's what I had as well. Here's how you would do it. Again, it's all about writing it down and knowing that multiplying by x shifts everything over by 1. Okay, so in this problem, new problem, now you have a new sum s, which is, what does that say, 0. 0 plus 1 copy of x plus 2 copies of x squared plus 3 copies of x cubed and so on. And like before, if you shift it over, things shift over. So you get the 0x, here you get a 1x squared, here you get a 2x cubed. And again, everything is getting multiplied by x is shifting over by 1. That's what the geometric stuff does. And now when you subtract, so you do a minus sign, on the left-hand side you get 1 minus x times s. And on the right-hand side you get some stuff. So you get 0, then you get an x. Then here you get 2x squared minus 1x squared is a plus x squared. Then you get x cubed, and so on. Plus dot 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 dot. And the thing is, we've done the sum here on the left-hand side. We did it already. When we did it before, we started at 1. So this is 1 over 1 minus x minus 1. And that's because the original thing here, that should have been a 1. But this is the sum we just did. And now you know the answer. You divide everything by 1 minus x, and you get it. So s is 1 over 1 minus x squared, and that minus 1 becomes a 1 over 1 minus x, which is the answer. So what is the moral of the story? When you have these big, long sums, as long as you're kind of moving over by multiplying by something, by x, in these geometric sums, you can often manipulate them and get a nice formula for the total sum. Anytime you can shift around the terms. And this is relevant to us because we have exactly one of these sums. We have over here, like we showed you on Desmos. Okay, I lost the Desmos. Okay, here it is. In Desmos, it looks like it says cosine. But I actually claim that the cosine is actually a power of something. It's something to the power k. And that is because we're actually working with e to the I kx. And if you think about it as e to the I kx, it's something, e to the I kx, all to the power k. There are different powers of something. And so the same shifting thing will give us a nice formula for this. So that's what we're going to start with. We're going to manipulate this thing and get a nice formula. I'll remind you what we were doing. So we had this nice formula, or we had this nice property, this kernel, and it looks like it's doing the direct delta thing, where it's all concentrating on a point. It's doing a sliding spike. In the middle there is a sliding spike we had earlier in the course. The sliding spike of width 1 over n and of height n that we've seen many times now. And the kernel we're looking at is very similar. So to remind you what is going on, this is all from last class. We did a bunch of algebra, and we got to the point that this sum, f0 plus fn divided by n plus 1, the average of the sum of the Fourier coefficients, or the Fourier approximations rather, right? This was like the Cesaro sum of the Fourier series, is the same as the integral of the original function against this kernel, and that kernel was the thing I showed you in Desmos. And then we had a path forward. We said this thing is called a summability kernel, and it satisfies these properties. And what we need to do is two things. We need to show lemma 3.5.3 that the thing we have is actually a summability kernel. It actually satisfies the properties we think it does based on the picture. So the properties say the total integral has to be 1, and it has to concentrate. So for any delta, the integral from minus to delta, that converges to 1. So it has all the properties we want. And the second thing we have to show is that when it has all the properties we want, it does the thing we need. So if it's a summability kernel, then it behaves like a Dirac delta in the limit as n goes to infinity. You integrate f of t against kn, and you just get back f of x. So you get the value of the function at one single point. So that's what we're going to do today, and we're going to, once we finish those two, we will prove that phi k is a complete orthonormal basis, and when phi k is a complete orthonormal basis, therefore Fourier series converge in L2. So f equals the limit as n goes to infinity of fn in L2, where fn is the sum, k going from minus n to n, of the inner product of f with phi k times phi k is the Fourier series with n terms, the n term approximation. So that's our main goal, is to prove this thing, and we're almost done. Any questions about the high level thing? So we're going to start with this little sum, and I'm going to show you a nice way to prove it's a summability kernel using the kind of algebra we were just doing. Yeah?
Did we at some point say that f does belong to L2 in this, are we assuming that, or is that not necessary?
Oh, yeah, does the original function f have to be in L2? So, yeah, this is a great point. If f is not in L2, so certainly if it's uglier than an L2 function, then nothing will make sense, because you're doing the inner product of f with phi k, and that only is like well defined for sure if f is in L2. Like the reason we know f phi k makes sense is because we do Cauchy-Schwarz, and it's less than the L2 norm of f times the L2 norm of phi, and it's all fine. So if f is in L2 or nicer, everything works. If f is uglier than L2, then there's no hope for this working. If the thing is, it's a great question, because if f is nicer than L2, then you get even nicer convergence. So you might hope for pointwise convergence or almost everywhere convergence, and those things are not true if f is an arbitrary L2 function. But if f is nicer, like if, for example, if f is continuous, then you get even nicer types of convergence. So there is a lot to be said about that, but we're doing kind of the most basic version of what could be the most basic thing that works. Yeah, great question. All right, any other questions or comments? Okay, so let's prove this summability kernel thing. And the first thing we're going to do is we're going to find a nice formula for this guy. Here's the nice formula, and it has a name in the textbook, which I will copy now, which is lemma 3.5.1, which is that the sum of k going from minus n to n, this is what we call gn of x. Gn is this sum of 1 minus the absolute value of k over n plus 1, which came from the Cesaro summation, and it's e to the I kx, but once again, you should think of e to the I kx as e to the ix all to the power k. It's something to the power k. There's some kind of arithmetic factor. There's some kind of geometric factor. This is really like an arithmetico-geometric series, like in the warm-up thing. And you can do the same kind of tricks to sum this up. And the answer you're going to get is very nice. It's 1 over n plus 1 times the sine squared of n plus 1 over 2 times x divided by the sine squared of x over 2. which is very surprising. You have some crazy thing, right? Big sum involving two n terms, summing from minus n to n, and at the end of the day, everything sort of cancels nicely, and you get a sine squared over sine squared. And you can check that it really works because you can check in decimals. So we can be sure that it's actually true in our days. Of course, Fejer, when he invented this, did not have decimals because he was born hundreds of years ago. But for us, it's no problem. You just put it in and you're like, hey, it works. Like, very nice. So let's see why it is. And I won't do like a super gory proof. Like I'm going to pretend we sort of know the answer and just show that it's true. But the way you discover the answer is the kind of trick we did just now with the arithmetical geometric series. You would shift it, you would take the sum, you would shift everything over by 1 by multiplying by e to the ix. Then you would shift over to the left by multiplying by e to the minus ix. And then you would watch a whole bunch of terms cancel. Very similar to how we were doing it before. So I won't give you the full thing. I'll just give you what's going on in the book. And so to start with, the sine squared of x over 2 is equal to the sine of, okay, let's do it the way the textbook does it. So first of all, they say this is the 1/2 times 1 minus the cosine of x, which is some trig identity. But the next thing that they really want is it is this, which you could also have gotten straight to here. Okay, yeah. Okay, so it's some linear combination of e to the minus ix, e to the ix, and a half. You could have also directly gone, because the sine function is e to the ix over 2 minus e to the minus ix over 2. That is one way to get sine. Oh, you divide, I guess you have to divide by 2. So if you want to know the sine of something, you can write the sine as a linear combination of e to the I and e to the minus I, and we're squaring it. And when you square it by the binomial theorem, you get that thing over there. So the sine is really shifting by down by 1 and up by 1 on our original sum. And now the textbook says literally the words, then routine calculations, which is always scary when your textbook says that. Okay. Routine calculations give, quoting verbatim from the textbook, if you multiply minus 1/4 e to the minus ix plus 1/2 minus 1/4 e to the plus ix, that's what we had, the sine squared thing, and you multiply that by the sum we're interested in, and I'm going to write the sum like this. I'm going to write it as n plus 1 minus the absolute value of k, and I factored out a 1 over n plus 1. So we originally had 1 minus the absolute value of k over n plus 1, but really these are arithmetic terms. They go n plus 1, n minus 1, and so on, all times e to the minus e to the ikx over here. So this shifts everything to the left, this shifts everything to the right, this leaves everything where it is. You do the shifting, and you're going to get a lot of cancellation. It's exactly like a slightly fancier version of what we started with, shifting everything over by 1. You have to shift in both ways and do a bunch of stuff. But the textbook says routine calculation equals ... equals 1 over n plus 1 times minus 1/4. What's left over at the end of the day after a whole bunch of things cancel? Well, you only have the sort of most extreme terms shifted again by 1, plus a half minus 1/4 e to the plus I n plus 1x. Right? So the sum, the most extreme thing in the sum was k equals minus n and k equals n. And then after shifting them, all the terms sort of in the middle canceled out, and what we were left with was n plus 1 and an n plus 1. And okay, it's not too hard to check. It is, quote, a routine calculation. And finally, this thing, like before, this is another sine squared. This is the sine squared of n plus 1 x over 2, because you have this kind of pattern of a sine squared. Okay, and this shows that when you take the kernel that we wanted and you multiply it by sine squared, you get sine squared of n plus 1 x over 2, and therefore the kernel that we want is the ratio. It's this thing, right? This ratio of sine squared of n plus 1 x divided by sine squared of x. Okay. So nice thing to do, and this is like a good tool in your arsenal. Like when you see sums like this, you should not be hopeless. You should be hopeful, because if they have arithmetic parts and geometric parts, you can handle those. That's the kind of thing you know how to actually sum. Okay. Next up, we're going to prove the properties of the summability kernel. Any questions or comments before we move on to that? Okay, let's prove the properties. And the three properties that we had to prove were this was from last class. So I guess lemma 3.5.2 says it satisfies these properties. And they call it Kn. Okay, let's call it Kn. I called it G, but we'll go with the textbook notation and call it K. Kn of x equals the sum from minus n to n e to the I kx satisfies. And the three things it satisfies are the integral is always 1, or rather the normalized integral, the average value is 1. The integral of the absolute value is bounded. That's equal m. And this is the big one. For all delta fixed, if you do the integral from, this is the way the textbook writes it, from minus pi to pi, but please skip over minus delta to delta. So everything outside of minus delta to delta, and then you integrate Kn of x dx, that is going to 0. So the limit is 0. The limit as n goes to infinity equals 0. And maybe I'll draw the number line here. So here's minus pi to pi, and you're saying integrate everything except for from minus delta to delta. That is where all the action is happening. The function is getting really super huge in minus delta to delta, and outside of minus delta to delta, it is kind of vanishing, going away to 0. So those are the three things we're going to prove. I will point out that number, in our case, because Kn is the particular thing we have, points 1 and points 2 are, point 2 is trivial, and that's because Kn is positive. So taking the absolute value, if you do the integral of the absolute value, that's the same as doing the integral of the actual thing. Not only is it going to be less than m, but n, capital M, will be equal to 1. For kernels that go up and down and are negative and positive, they can be quite a bit more complicated because they sort of have cancellation. But our kernel is a positive thing, so it's trivial. Number 2 is an easy one. Why is it positive? Well, the reason is we showed that this was sine squared, right? And the sine anything squared will be positive. So it's clearly positive because it's made of sine squareds. Okay. What about the integral, the first integral? Why is the integral equal to 1? So again, you could use our identity and try to do the integral of sine squared, and you would eventually get it. But it's actually even simpler than that. So here's the proof. Let's give these names 1, 2, and 3. And the proof of 1. You could take our formula, but actually it's even easier because remember, it's the sum from k equals minus n to n of 1 minus absolute k over n plus 1. And then we're integrating e to the I k x dx. And the integral of e to the I k x dx, this is the kind of integral we did last time, this integral will always be 0 as long as k is not equal to 0 itself. So when k is equal to 1 or 2 or 3, this integral is 0. The only term that survives is when k equals 0. And when k equals 0, this coefficient is exactly 1. So you could write it like this. 0 plus dot 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 plus 0 plus 1 plus 0 plus dot 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 plus 0. This is k less than 0. This is k bigger than 0. And the only surviving term is k equals 0. And that coefficient is exactly 1. Oh, let me put a 1 over 2 pi. Right, okay. Then it's totally fine. So because we made it of these simple parts, of course it comes out to 1. That one's not actually a surprise. That's 1. 2, I said it's trivial. Trivial since Kn of x is greater than 0. And 3 seems like it could be quite a bit of work to prove. Why is it true that the integral is going to 0? But actually, because we have a nice representation for the function, in terms of signs, the proof is going to fall out of the fact that the function sign is just increasing. So we're going to look at for absolute value of x bigger than absolute value of delta. So that's anything inside our intervals. So any x in here, outside of these things. We know that the sine squared of x is bigger than the sine squared of delta. Let me make sure I got it in the right spot. Yeah, so the sine function is monotone increasing from 0 to pi. Is that right? That sounds
Isn't it?
maybe only up to pi by 2.
Yeah.
Okay, hold on, yeah. Ah, okay. Remember, it's not sine of x. Sine of x divided by 2. Okay, so, okay. And you could say because sine is increasing on 0 to pi by 2. Okay, that's great. So that's good, we did it right. So if the sine squared is bigger, then you're dividing, when you do this denominator, you're dividing by a big number that's bigger than the sine squared of delta over 2. So we're going to have a nice inequality that kn of x, which is 1 over n plus 1 sine squared of n plus 1 over 2 x divided by sine squared of x over 2 is less than what happens when you replace the bottom with sine squared of delta over 2. And then you have sine squared of n plus 1 over 2x. Okay. So when you integrate this stuff on the outside, it's bounded above by dividing by the sine squared of delta over 2. Okay. Not only that, I can also find an easy bound for the top bit. The sine squared. Remember, I'm trying to prove that the integral is going to 0. So can I bound the top by something in a way that doesn't give away too much? I can just bound it by 1. So less than equal to 1 over n plus 1 times 1 over sine squared of delta over 2. Okay. So the whole function is going to be less than the sine squared of delta over 2. We can visualize what this thing looks like on Desmos. Okay, let's pause this for 1 sec. And let's do, I'm going to use d for delta. Let's make that 0.1. And then let's do the function 1 over n plus 1 times 1 over, well, let me do 1 over the sine squared of delta over 2. Okay, and I want the function y equals that. Am I forgetting something? I'm forgetting a 1 over 2 pi. Am I? Let's go look. Sine squared? No, there is no 1 over 2 pi. Oh, okay, yeah, there is a 1 over 2 pi because I probably didn't write a 1 over 2 pi in Desmos. Sine, cos. It's equal to that. Okay, it's true. I mean, what did I want to show? The purple function is less than the blue function. It's working. It's just not a very good inequality. Okay, so that's great. So as you make n bigger and bigger, these things get closer and closer together. So the inequality gets better and better as n gets larger. Let's see. Okay. So, and look, you might say, oh, the inequality is violated. But remember, we're only proving it on the interval minus delta to delta. So on some small interval, right, near 0, the inequality is not true, but outside of the interval, it's fine. I guess I should draw this interval. Minus d less than x less than d. That's what I want. I think I made Desmos explode by putting in such big numbers. But so on this interval, the function is huge, and that's fine. It's just that outside of this interval, we're bounding the purple by the blue, and everything is working just fine. And you can see that it's actually a very good inequality when n is extremely large. It's like pretty close to right on. When n is small, it's not a great inequality, but that's fine. Okay, so this is the kind of thing if you're like really doing analysis, these are the kind of inequalities you stare at for a long time and worry about getting the inequality signed the wrong way and that kind of thing. This is a clever one. So this is a nice bound on kn of x. For x, exactly, only on the intervals we care about. Only the x's that we care about. And now when you go to integrate it, so you do the integral. Technically you should do the integral of the absolute value of x, but because it's always positive, that's fine. So x bigger than delta is less than the integral of x bigger than delta of 1 over n plus 1 times 1 over the sine squared of delta over 2. And the integral of sine squared of delta over 2, that's some number. Like, we don't even care what that is. So this whole thing is 2 pi divided by the sine squared of delta over 2, which is some number. For delta very small, maybe that's a huge number, but that's fine. For any fixed delta, that's okay, because we have a 1 over n plus 1 in front, and the limit of that is 0. So the limit of any number times 1 over n plus 1 is 0 as n goes to infinity. So that's a nice little bit of like very practical analysis on this function, bounding it by simple things to get what we want, that it's going to 0. All right. And that proves 3. Okay, any questions or comments about that? Yeah?
Do you mind explaining the proof of point 1 again?
Yeah, let's do point 1 again. So point 1 just says the total integral is 1. And the thing is that Kn is made of a sum of many functions, one of which is exactly the function 1, and you integrate it, you get 1, and a lot of other functions that integrate to 0. And so the things that integrate to 0 are, it's the integral of e to the ikx. The integral is 1 over ik e to the ikx. And then when you put in pi and minus pi, because e to the 2 pi I is 0, you'll just get 0. This is the same reason that we said they were orthonormal last time. And you can do that as long as you don't divide by 0. So as long as k is not 0, they're integrating to 0. Another way to think about it is they're like sine of kx and cosine of kx, because sine and cosine are periodic, they're going to integrate to 0. And the only exception is when k equals 0, then you have the function 1. And then it really doesn't integrate to 0. Yeah, no, this is like worth understanding and doing nicely. And it is, like, you could spend a lot of time doing the integral of this nasty function. And if it's going to work out to 1, but it's going to be annoying. Whereas if you write it the way like this, then it's a snap. So it's a good lesson on like thinking about the function in different ways when it's convenient for you. Great question. All right, anyone else? Okay, so now we've completed half the path, half the critical path here. So we've done this lemma. Got it? Now we're going to work on this one. If it's a summability kernel, then you get this Dirac delta property. So anything that satisfies, any kappa n that satisfies those 3 properties, that it integrates to 1, that if outside of minus delta the delta is converging to 0, that will be this Dirac delta property of getting back the original function. And this is one of the most intense analysis proofs of the whole course. So let's do it. Now, this is theorem 3.5.4. And yeah, I could not understand what they said in the textbook, so I made it my own proof. Hopefully it'll be more clear than the textbook one. Okay, theorem 3.5.4. And again, to me, this one has the feel of like what it actually feels like doing analysis on like a research project, where you're looking at things, you're like trying to think about where things are small and where you can bound things and get what you want. All right, so we're proving we're going to let Gn of x is the function 1 over 2 pi times the integral minus pi to pi of kappa n of t times f of x minus t dt. Yeah. So it's the integral of the function f. Okay, I did a swap here. I think we had it originally written like this, minus pi to pi of f of t, and then I said kappa n of x minus t dt. So I did a swap here where I wrote one of them with a t and the other one with an x minus t, and then in this one I wrote the f with a t and the kn with an x minus t. Yeah.
Are those gn you were calling fn before?
We were calling them fn before. Yes. Yeah. So I guess in this theorem, right, kappa n is any summability kernel. And we're proving that for any summability kernel it works. In particular, it's going to work for ours. Yeah. Yes. Okay, so I did this little swap here. If you've done convolutions before, you'll recognize both of these things are the convolution of f star kappa n evaluated at x. And so like they have to be the same, otherwise a star operation doesn't make sense. If you don't know convolutions, it is just a simple change of variable plus thinking of the function f as being periodic. So all it is a change of variables, like t is x minus t, but you do have to think of the function f as being periodic. So like what happens if you do f of pi plus 1? Well, just think of that as being the same as f of 1, and then it's all fine. So far f has been just a function on minus pi to pi, but just imagine that if you go past pi, you come back around at minus pi. So think of f as being periodic. And so for example, e.g. f of pi plus 1, technically that wouldn't be defined, right? Because f is only defined up from minus pi to pi, but just imagine that's f of 1. So every time we have to do an integral where we kind of like scroll past, we just loop back around. And then these things make perfectly good sense, and they're just fine. Yeah.
Is f pi periodic or is it 2 pi periodic?
Oh, it's periodic, I'll say, on minus pi to pi. So it is 2 pi periodic, but I want to think of the like actual main interval as from minus pi to pi, not from 0 to 2 pi. Yeah.
Oh.
I'm looking at those convolutions on the Fourier line. So is
Yes.
1 over 2 pi part of the convolution here? Or is it a
Yeah, this is true. So this is a convolution on this like periodic thing from minus pi to pi. You can think of it as the circle. You can think of it as the circle. So you can think of f as some function that lives on the circle, and we're doing the convolution over the circle. The 1 over 2 pi is totally harmless. It's just making it so the integral of the function 1 is 1. Otherwise, the integral of the function 1 would be 2 pi, and that would be annoying. So if you want, you can think of it as the average value. Actually, in some textbooks, they'll write like this. They'll write the integral bar, which looks like an f. Okay, this is a disaster. The integral from minus pi to pi bar, that means 1 over 2 pi times the integral from minus pi to pi, and that's because it's the average value. Yeah. Okay. So that's the function gn, and why did I did this sneaky switch. So instead of integrating against f of t and then doing kn of some nasty stuff, I'm integrating kn of t and then I'm shifting f by just a little bit. Okay? And the reason I'm doing this is because now, if you write down gn of x minus f of x, it's going to be something that looks very promising. Minus pi to pi, and then there's going to be 2 parts. There's kappa n of t, and there is f of x minus t minus f of x dt. Yeah, okay. And here what I'm doing is I'm writing, since f of x equals this integral. The integral of kappa n on its own, that integral is 1. So I'm writing f as 1 times f, and then this integral is nice because it lets me directly compare gn and f. I can write them both as integrals against this thing. All right. And now is where you can start to sort of feel like you can imagine having this on your page and trying to get to the proof. We're trying to prove that this thing, gn minus f, is going to 0. We want this to be small. Why should this thing be small? Well, there's 2 things that are 2 ingredients. There's the kappa n, and then there's f of x minus t and f of x. And kappa n and f, they are both sometimes small, and when one of them is small, the other one might be big, but when the other one is big, the first one is small. When is kappa n small? Kappa n is small for t bigger than delta, right? Outside of minus delta to delta, kappa n of t is something that integrates to 0. That's what we were just talking about. So this kappa n function, it's doing this big spiky thing. So except for t values really close to 0, kappa n is so tiny, hopefully it doesn't matter. Right? So that covers all the values except for really small values where t is a super tiny number. When t is a super tiny number, then hopefully this stuff will be small. This will be small. This will be small. When t is tiny. Right? So the kappa n, because it has this property of the summability kernel, for t outside of some delta, is going to be really tiny, and that'll bound that. And then hopefully f of x minus t minus f of x, you can imagine why that would be small when t is really small. You've taken the function f and you've shifted it by a tiny bit, and then it should be like almost not doing anything. So this is the main idea. So the whole proof now is going to seem like a lot of crazy analysis, but it's just trying to extract out these 2 main ideas. We're going to take some stuff here, we're going to split it into 2 parts. One where this is the thing to bound, and one where that thing is the thing to bound. And we're going to bound both by epsilon over 2. The whole thing will be less than epsilon. That's the main idea. There's going to be some, some tricky, annoying analysis stuff, But maybe this is a good place to pause for questions about the main idea of the proof. And this is like how analysis proofs are discovered in the wild. You think of something like this, and then you do like 2 pages of work to really prove that it's true. But first you have to have the idea. Without the idea, you'll never get the proof. Questions? Okay, so let's do it. The first thing is we don't want to prove this for every x, because it's not going to be true for every x. We want to prove it in L2. So we're going to actually integrate the left-hand side. Then this is gn minus f. We're going to take the norm of both sides, and the norm means doing an integral. Okay, and I think we're going to do the L1 norm. So we're going to prove the L1 norm. So the norm of gn minus f is the integral of everything we just had, integrated over x. Integrated over x. So I'm going to write it like this. Okay, before I write it, I'm going to give this thing a name. Yeah, because when I integrate over x, this thing becomes a little annoying. So I'm going to give this thing a name. I'm going to call this thing tt of f minus f of x, where t is the shift operator. Tt of f is the function f of x minus t. T is the shift by t operator. So it inputs the function f and it outputs a shifted version. And okay, you'll see why I wrote it this way. I could have written f of x minus t everywhere, but then it gets annoying when you want to take the norm. When you take the norm of f of x minus t, you write norm of what, and then it's like annoying to write, whereas if you write it this way, it's the norm of tt of f. Everything makes perfectly good sense. It really is just to save my notation when I start writing norms. So hopefully it's not too bad. It's tt of f minus f evaluated at x, the shifted version of f, minus f evaluated at x. And I'm going to do the norm. So when you do the norm, you're going to integrate up. You do the absolute value of all this stuff, and you integrate it. So you should really imagine we're doing the integral from minus pi to pi of absolute value of all stuff of x dx, where all stuff means everything in there. I just need to upper bound it. I just want it to be less than pi, so I'm going to write it like this. I'm going to write it in the following way. It's less than or equal to 1 over 2 pi, and then you integrate from minus pi to pi of the absolute value of kn of t. So you see, when you do the integral here, the kn, when you're integrating over x, there's no x's. So you just kn of t. It's always kn of t. You can pull the integral with x inside. And then over here, you're going to have, still in this integral sign, you're going to have the integral from minus pi to pi of tt of f minus f of x in absolute value dx. I want the dx like this. And then dt. Maybe it helps to do some colors. Let's do dt. This is the dt integral on the outside, and this is the dx integral on the inside. Okay. Okay, and very technically speaking, if you want to justify these steps, sometimes you have to be a little bit careful about the order of the integrals and stuff. But when we're proving it's less than 0 in absolute value, it's going to work out. So I'm sort of skipping some very technical steps about the order of integrals and stuff like that. But they're all fine. This is the kind of thing I want to do. And the reason I want to do it is because the thing in brackets here is a norm, and then I can just have one less integral. So then I have the integral of 1 over 2 pi, and then now I'm just back to integrating in t. Absolute value of kn of t. And then this thing is the norm of tt of f minus f dt. Okay. So for every t value, you have the absolute value of kn of t, and then you have this norm, which is the norm of tt of f minus f. That's the norm of how much f is far away from the shifted version of f. Right? You shift f by a little bit, and then you say how far is that from the original function f. And this is the integral that I'm going to bound. This is where the intuition is really going to apply. We're going to have these two parts. I'm going to split this whole integral into two parts. So there's going to be less or equal 1 over 2 pi. Then I'm going to do the integral from minus pi to pi, but not minus delta to delta of the same stuff. Okay, tt of f minus f dt plus, then I'm going to do the integral from minus delta to delta of the same stuff. Kn of t, norm of tt of f minus f dt. Okay? And in the first part of the integral, the kn is going to be small. Actually, I can do this one right away. This is less than or equal to 1 over 2 pi times the integral from minus pi to pi. Take away minus delta to delta, kn of t, absolute value, dt, and then this norm is less than something. This is less than, say, the maximum over t of the norm of tt of f minus f. There's some value of t that is the worst one, just bounded by the maximum. And the point is that this first part, goes to 0. This is all for this first little bit here. Since kappa n is a summability kernel. So this is property 3 of the summability kernels, that they go to 0 on the interval minus delta to delta for any delta. Yeah?
Why do we have less than or equal to sign when we split the two integrals?
So okay, I'm only working on, all this stuff here is only the first part. Okay, let's be really clear. I'm going to work on this part separately in a second. This will be a separate piece of work. You're saying, why is there an inequality going from here to here, or a different inequality?
Previous step.
Okay, why is it going from here to here? Okay, you're right, it is an equal sign. Okay, sure. Okay, yeah, I agree, that can be an equal sign. Yes, okay, very good. Any other questions? Okay, so basically this one does like what we want. The summability kernel is exactly defined to make this one be okay. The nice thing is this norm can never be too big, right? Like for example, you could do triangle inequality. The norm of tt of f is equal to the norm of f. So this whole thing, right, is less than or equal to 2 times the norm of f by triangle inequality. So it definitely can't be too big. So that's totally fine. The integral of the kn outside of minus delta delta is totally fine. How are we going to deal with this one? Well, in this one, the kn is not going to help us at all. We're just going to throw away the kn, and we're going to use the fact that tt of f is close to f. So there is a fact, and this was a lemma way back in our Lebesgue integral days. What lemma is it? Oh yeah, theorem 2.4.3. This was when we just started Lebesgue integrals. The limit as t goes to 0 of the norm of tt of f minus f, that norm equals 0. So as t goes to 0, the shifted version of f gets closer and closer to the original function f. The proof of this lemma is exactly one of those really annoying proofs we did in Lebesgue integrals, where you just prove it for step functions, and then you prove that if it works for step functions, and then f is made of an infinite sum of step functions, it's going to work for f too. And you just have to truncate by epsilon and that kind of thing. So I won't do the full proof. But what this means is that this integral, in there, the norm of this thing is getting closer and closer to 0. And so we'll just pick a delta that's small enough so that it can bound everything else. So we're going to do this. Okay, so I think what I said is, by theorem 2.4.3, given any epsilon greater than 0, find delta so that the limit as t goes to 0, the norm of tt of f minus f is less than, not the limit, just the actual thing, is less than epsilon over 2, and then I want to make it even smaller, epsilon over 2 times the integral from minus pi to pi of the absolute value of kappa n of t dt for all t less than delta. It's the absolute value of t less than delta. And actually, why don't I make this thing, let me just squeeze a little thing in to make this super clear, epsilon over 2m, which is less than this. So you remember, part of the rules of the summability kernel is that when you integrate its absolute value, it's less than some constant m. and that is the m that I want. That is less than that. Yeah, okay. Yeah.
Would the n matter when it changes?
The m?
The
Oh,
n,
the n, yes.
Okay.
The n, so the n would be a problem, except I'm just actually, okay, let me do it in 2 steps. I think I basically wanted to do 2 things at once. Let's do this. You're pointing out a good, let's be clear. Okay, where m is the constant, so that integral of absolute value of kn of t dt is less than or equal to m. So this was bullet point 2 of the summability kernels, so that there is a capital M where this works. And I'm doing epsilon over 2m. And then I will do as a conclusion, I will say, therefore, tt of f minus f is less than epsilon over 2m is less than 1 over 2 times this integral, kappa n of t dt, for all n. Okay, so normally you're not allowed to make this depend on n or anything else, but because they're always bounded with this constant m, then it's okay. Okay, and this is using bullet point 2 of the kernel case. So far we've used bullet point 2 and bullet point 3. Actually, we used bullet point 1 earlier on. We used it over here. This was bullet point 1. So now we've used all 3 properties of the summability kernel. Okay, so tt of f minus f is less than epsilon over 2m, which is less than this stuff. And therefore, with this delta, if you do the integral from minus delta to delta of absolute value of kn of t times the norm of tt of f minus f dt, for all of the t's in this region minus delta to delta, this norm term is always less than epsilon over 2m. So you get less than the integral minus delta over delta kn of t, let's say dt, times 1 over 2 times the integral. Epsilon times that. Okay, there should be an epsilon in the front. Okay, so the whole thing, you have integrating from minus delta to delta, dividing by integrating by everything. That's definitely less than 1, and you have an epsilon over 2 left over. Less than epsilon over 2. Okay, so in this story, we found a delta, so that as soon as you choose the delta small enough, the whole integral here is less than epsilon over 2. And then, if we were doing this properly, we would go back and say, now that we've chosen the delta for this side to work, we know that this side works for any delta. So take the delta that works for the green arrow, that's some fixed delta, and then this orange argument will work for that delta. This will be going to 0, it'll be less than epsilon over 2 eventually, and then we're fine. So you could write that all up. If I was smarter, I guess I would have done the proof in this order. But when you're doing real math, like you often do it in some wacky order, and then you write it up nicely in one order at the end. Or you split it up in dilemmas or something so that there is no order. Okay, but that's the whole proof. Okay. So both pieces eventually less than epsilon over 2. Okay. Questions or comments about this one? Okay, because I have a little bit of extra time here, I think we're going to finish. Let me show you this stuff in the wild. If I can find my mouse. Give me 1 second here.
So it's integrating the same function, and the function is positive, and this one's integrating over a bigger range. So this integral is bigger than this integral. So then this over this would be less than or equal to 1 over 2 because there's a factor of 2, and the epsilon stays on top. Exactly. Yeah, so like you integrate
Okay.
over here, it's bigger than integrating over here.
Okay, here is a fun document called Thesis Final. On page 137, which is on page 147 of the notes, there is a nice splitting of these spaces D1, D2, D3, D4. What is this document? This is my PhD thesis. Okay, and it really is doing exactly what we just did. So
My brain is melting.
on page 137, let me find it again. The whole argument, we're trying to show that some integral converges to some other integral, exactly like we're doing. The integral on the left-hand side is some integral over r with t, and the one on the right is some sum over some like finite set of entries. So you're doing a big sum, it's like a Riemann integral. And for parameters delta, eta, and m, we split up the integrals into 4 parts. There's this d1, d2, d3, and d4, okay? d1 is where the absolute value of z is less than m, and there's a delta to minus delta, exactly like we were doing. So t is between delta and t star minus delta. So t is not, it's in from delta to minus delta. And then over here in d3, we cover the place t star minus delta to t star. So this is like very close. When you're between 0 and delta or within delta of the n, that's d3. So we kind of did the split d1 and d3. In this thesis, you have to do d1, d2, d3, and d4. And there's basically like a whole chapter proving it for d1, proving it for a different chapter, proving it for d2, a third chapter proving it for d3, and a third chapter proving it for d4. And like all of them are less than epsilon over 4, and then you put it together and you get the proof of the theorem. So basically we did a version of that and over here, where we just had a d1 and a d2, right? So we had over here, this was our d1, this was our d2, and we kind of worked on them separately, and they're small for different reasons, right? So this kind of stuff is like real life analysis. It's like a baby version of how you really do real analysis. Okay.
This is like, I don't know, I like it how I've been doing this for like 3 years now, and I still compare myself with like moves.
Yeah, 3 years is not a long time to be doing
Yeah.
it. This is it feels like a long time. But yeah, as you go, you sort of like get an intuition on these kinds of ideas of like, okay, we have these different parts, and if we split it up on this part, you get one thing, on this part, you get another thing. This is like a very real type of argument that occurs in the wild all the time, at least in my area of math. Okay, so let's go back to our little roadmap and see what is left. There's almost nothing left. We have done the things we wanted. Okay, so we've done lemma 3.5.3, we've done lemma 3.5.4. So the thing that we wanted is a summability kernel, and summability kernels have the Dirac delta property. And we're going to put that together to prove that the limit as n goes to infinity of f0 to fn divided by n plus 1 equals f in L2. And it's actually a very short proof. We've almost done everything. Okay, so does this thing have a name? Oh yeah, theorem 3.5.5. The limit as n goes to infinity of f0 plus dot dot dot. Oh, okay, sorry. Yeah, okay. Okay, the theorem I told you is slightly different, but it's essentially this. Okay, this of f0 plus fn over n plus 1 equals f in L2, and the proof is quite simple. The left-hand side is equal to the integral of kn of t f of x minus t dt. To the left-hand side, as a function of x, is equal to that, minus pi to pi, with kn. The Fejer kernel, that's the thing we've been working on. So that's what we showed, that's how we started. This sum is actually the integral against kn. And we showed that it's a kernel, and therefore it converges. So therefore, by theorem, whatever it was, 3.5.4, it converges to f in L2. Okay, so just a nice way of saying, look, we did all the stuff that we had to do. This converges to that. And then there is another result that this is what we actually wanted to prove, which is theorem 3.5.6, which is that phi n is an orthonormal basis. Phi, I guess we've been calling them k's. Phi k is an orthonormal basis. And we're going to prove it by doing the criteria we showed before. We'll show that the only function f with inner product of f phi k equals 0 for all k is the zero function, is f equals 0 in all t. So this was a theorem. Did I write down what it is? Yeah, this was theorem 3.4.14, where we said something is an orthonormal basis if and only if the only vector whose inner product with it is 0 is the 0 vector, right? If you're missing some vectors, like if you have sines and you forgot about cosine, then that's not a complete orthonormal basis because you're missing the cosines. Yeah, I'm missing the word complete here, which is important. Complete. But if the only vector whose inner product is 0 is the 0 vector, then it's a complete orthonormal basis. That's what we're going to do. Okay. Suppose f is such that the inner product of f phi k equals 0 for all k. We want to conclude that f is 0. Notice f0 plus f1 plus dot 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 plus fn divided by n plus 1 is 0 in this case. Right? So the functions f0, f1, fn, they were made of coefficients of the form f phi k. And so if f phi k is 0 always, then you do linear combinations of them, this function will be 0. And this is for any n, Okay. On the other hand, we just proved that this thing converges back to f, right? Therefore, the limit as n goes to infinity of f0 plus f1 plus dot 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 plus fn over n plus 1 equals 0 in L2, right? If it's 0 for every value of n, then you take the limit of 0. What's the limit of all zeros? It's the 0 function, again, in L2. On the other hand, by theorem, the previous theorem, by theorem 3.5.5, the limit is 0. The limit is f. Okay. F0 plus f1 plus dot 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 plus fn divided by n plus 1 is equal to f. Therefore, f equals 0 in L2. So if the limit is 0, because it's always 0, and the limit is f, by the theorem, therefore f equals 0 in L2. Okay. So very simple result. Nothing, no analysis here, just putting together the sort of easy facts. Okay. And so last but not least, I guess we're done because so we have it's an orthonormal basis, and I guess this is a corollary, which is the convergence of Fourier series in L2. So if f is in L2, then the Fourier series converges in L2. In L2, f equals the limit as n goes to infinity of the, let's write it as fn, and fn is exactly the sum of the Fourier series with sines and cosines up to order n. F phi k, phi k. Okay, and this convergence is in L2, so in the L2 norm. In the textbook, they write another fun fact for you, which is they say, let me see if I can get the fun fact from the textbook correct. I'm in some weird search here. Oh, the textbook does not like me anymore. Okay. Single page. Okay, here we go. There's a fun fact. I want to get the date right for you. Orthogonal projections is complete. Okay, yeah. So yeah, here's the relevant line from the textbook. So okay, so this is the convergence of Fourier series. The series is called the Fourier series, and the number are called the Fourier coefficients. So they converge in L2. You also have nice things like the Percival formula, So if you take the L2 norm of f, that's equal to the sum squared of the Fourier coefficients. That was exactly what we called Bessel's equality before. But the fun fact I wanted to show you is it is important to remember that in general, the equation 3.4.1, that's the convergence, does not imply pointwise convergence. So we have L2 convergence. On average, they converge. But maybe there's like a lot of points where they don't converge, right? The problem of pointwise convergence is much more difficult. Okay, and it was only proven in 1966. So this stuff goes back to Fourier. It was like hundreds of years. The proof we just saw is by this guy Fejer, who was born around, like he was working around 1900, and it took until 1966. This guy Carlson proved that the Fourier series, if it's an L2 function, it converges almost everywhere. So there can be like points of discontinuity. It can not converge. So in fact, I think we started the course with an example of a jump function. That is a step, and right at the jump, it won't converge. But that's just a couple of points. So almost everywhere, it will converge. And it converge. We showed that it converges in L2. You can keep going with these things. If the function is continuous, I think you get even stronger convergence and stuff like that. Okay, this is the main quest of the course, was to prove this, and we've proven it. So I think this is a good place to stop. And on Thursday's class, we'll start presentations from students. Please do come for that. It'll be nice to have a little audience. And so we'll see you guys Thursday, and next week will be all student presentations. Okay, I'll stop there, and we'll see you guys on Thursday.
Does the write-up for the draft have to be double-spaced?
Oh, I don't know. It does not have to be double-spaced. That's fine.
Can it be double-spaced?
If you want to, yeah, sure. Yeah.